Okay, so I'm Logan from Zorp. Zorp's a big old team now. I think we're at 10 now. We are a Nock company, and we're building the world's best general purpose verifiable virtual machine. Okay, so let's break that down a little bit because all of those words mean something, right? So everybody here knows that you can do general purpose computation with urbit and with Nock. You can do things like networking. You can do things like building games, like we just saw from Jake. You can do things like building collaborative document editing. You can build chat. You can build gossiping rumors applications. You can build friends lists. You can build persistence. You can build build systems. You can build arbitrary system computation, arbitrary user space computation. We all know that. A lot of people, well, they work with languages that aren't as general purpose as ours. And so it's really, really worth kind of nailing down specifically what we're up to over here with Nock, all of us together. Okay, so Zorp has made Nock not just a really strong general purpose virtual machine that could realistically one day run on your phone and your server and your laptop, your blockchain, your whole deal, but Zorp has now made Nock verifiable using zero-knowledge proofs. So Zorp has made it possible now for us to take this general-purpose virtual machine, not some, say, you see a lot of ZK companies today that make blockchain-specific zkVMs, like say Cairo as an example. People that are building languages that are very specific to just the purpose of doing verifiable, provable computation. What we're doing is quite different than that, and there's really only one or two other people that are even doing anything remotely similar, which is we're building general purpose verifiable virtual machines, or the ability to take anything, any computation, in any context. Now, of course, it would need to be targeted towards Nock and make it verifiable. And by verifiable, what I mean is that you don't have to trust it. You can very, very succinctly, simply, quickly verify that a particular computation was done with some particular input and received some particular output with very, very little work to do the verification, very, very little data that needed to be transmitted in order to do it, and absolutely no trust. So I know we're all Nock partisans here, and this is a little bit of why we're here. I know many people are also urbit partisans even more than they are Nock partisans. But we strongly believe at Zorp that Nock is the perfect VM for ZK, blockchain, and everything else. We think that urbit is this everything else, more or less. And we think that that's wonderful. So Nock is perfect not just because it's small, not just because it's minimal, not just because it's built on binary trees. Nock is perfect because it's highly structured. It's a homoiconic pico-Lisp built on a single data structure, which is able to efficiently and succinctly build Turing-complete computation without throwing you into the hell that is lambda calculus. Okay, so we don't want to be in lambda calculus hell, but we want to actually understand what our computers are doing. Okay. So the claim with Nock is that the way to understand what the computer is doing is not by building more and more complex abstractions, but rather by simplifying the base layers down to a level that can act as a specification for what should be happening, that is actually cognizable, that a single person can then inspect and understand. And so we strongly believe in being able to understand what's happening. So in that vein, we're going to get a little bit in depth into how our ZK proofs work today. And then we can go a little bit even more into what's so awesome about us, which is, well, wow, this is going all over the place. Okay, so similarly, I'll give you a little bit more on Nock, and then we'll get into the juicy stuff. So what we see in the ZK space in general is, well, there's a hell of a lot of people trying to build ZK VMs, et cetera. But most of them really aren't that good in various ways. And so what we find is that we have maximum expressivity in Nock and Hoon. And by that, I more or less mean maximum developer productivity when working with the language, because it's extremely expressive and easy to work with. We also have maximum efficiency, and I'm going to get to why that's the case, because that's a large part of what this talk is going to focus on. But we also have maximum generality. In other words, the language we're working on, I've already hit upon this, is really, really good for a variety of contexts. It's not just some tiny little domain-specific language that's only good if you're doing ZK. It's not only good if you're wanting to do blockchain stuff. It's not only good for smart contracts. It's not only good for urbit. It's just really good. And so in this little schema of generality, efficiency, and expressivity, Nock is maxed out in every degree. And everybody else is lacking in some dimension or another. So getting into some of the juicy bits of, well, what makes Nock unique in a ZK context? Well, the high-level answer is that we've liberated zkVMs from the von Neumann style. This is a little bit of a play on a paper that some of you may recognize. But the point here, the thing that's interesting about this, is that Nock is a pure function. It's a pure function with a single data structure. And not only is it a pure function with a single data structure, but it's a pure function where every single transform from one data structure to another, or one state to another, is a cognizable step from a single data format, which is really, really beautiful, but also that all of these operations reduce down to a very, very easy to model operation, which is concatenation. Trees and other Lisps, but trees particularly, get really performant concatenation, because almost anything that you want to do is going to reduce to log n time. So this provides us a bunch of wins, and we're going to go look at many of them. But I'm going to give you the payload to start with before we get into the dense stuff. And to start with, memory editing, really great. Memory retrieval, really, really great. Deduplication of reused memory objects across the computation. We can do it automatically on the back end. Easy ability to decompose and destructure operands without needing to resort to really expensive things like, say, Merkle trees. We get it. Many other different traits here we can get in very, very powerful ways. And we get to represent the abstractions that Nock is using and the invariance that Nock needs to maintain across the computation with extraordinarily minimal primitives. I don't know if any of you have interacted with any ZK research papers, but they're dense. It's not always a bad thing. A lot of them are really, really, there's a lot going on. But, well, I mean, necessity is the mother of invention, yeah? I mean, if you're trying to fit a square peg through a round hole, you're going to need to invent some really freaky math if you want to be able to do anything with it. We're in a lovely situation where we've actually been able to get best-in-class results with very simple primitives without even doing these more complicated transforms, which we're now in the process of implementing. Okay. So let's talk a little bit about binary trees. Can someone move this picture of me over there, or get rid of it? I don't care. Okay. All right, so we've got a binary tree, right? This should be fairly recognizable to many of you, right? We've got something on the left. We've got some stuff on the right. Turns out that we don't need to represent this in the naive way that we might be inclined to, or that we might be used to veer representing this. We don't need to represent this binary tree as a series of pointers. The naive way to handle this is to say, okay, this is our state. This is going to have a pointer to this. This will be a direct atom. This will have a pointer to this, which will have a pointer to this, which is a direct atom, pointer to this, pointer to this, direct atom, pointer to this, direct atom. Veer is able to do some tricks with this to make this not horrific, which is it's able to do a bunch of deduplication so that at the very least you don't need to store many, many copies of some of the same large atoms or things like this. But there are things that we can do in a ZK context that are far more efficient than dealing with pointers, which are to reduce this structure down to a pair of vectors. Now, you can also do this natively in Veer if you want to, and it's actually really, really useful in some contexts, and I expect that Aries will at some point implement perhaps this strategy, perhaps a similar strategy for some data structures, probably with some intelligent analysis around when to do it and when not to do it. You might imagine it, if you're kind of an interpreter guy, as being somewhat akin to V-lists, but really, really generic. Okay, so we're able to separate this binary tree structure instead of having to represent the links between the different nodes explicitly with pointers. We're able to separate it into a shape vector and a leaf vector, right? So let's start with the leaf vector because it's super obvious. We can see that the leaf vector is a depth-first traversal of the tree. You have your 0 on the left, then you go down to the right, then you go left, left, now you're 6, up, right, 20, up, right, 1. Okay, so the shape vector's a little bit more involved, but not too bad. So the shape vector is built on a recursive relationship found in combinatorics called dequards. And so that's wonderful because you can actually build this up also with a depth-first traversal of the shape of the tree. So let's kind of examine the left-hand side. With the left-hand side, we have an atom. In a dequard context, that's empty. You don't need to put anything there. So we slap a 0, an empty, and a 1 to say we're going to cons something. And then we just start expressing the right-hand side. So the right-hand side, we go left, 0, we go left, 0. We close with a 1 because 20 and 6 are atoms. So we say 1, then we go up, and then we say 1 again. So at a high level, this 0, 0, 1, 1 represents the right-hand tree structure, and the left-hand tree structure is represented by an empty, but because it's concatenated to the right-hand side, you have a 0 and a 1. Okay. So a little bit more involved, but there's a recursive relationship. You can always build up more valid dequards just by consing existing valid dequards to them, with the caveat that you need to put a 0, then the left-hand side, a 1, then the right-hand side. But still, really, really simple cons relation. We're going to get to this. Okay, so the first transform we did was we turned our binary tree into this pair of vectors. The second transform that we're going to do is we're going to express the length of the number of leaves, we're going to express the shape, and we're going to express the leaf in terms of finite field arithmetic. Okay, so we're going to pretend that instead of this being a vector, it's actually a polynomial. And I'm not actually transforming anything, I'm just saying let's think about it a little bit differently instead, right? So if you look at this, you can say, okay, well, if you kind of start from the bottom, you can see there's a 1, okay, there's a 1, so 1 plus x, right? Then there's a 0, so that would be x squared, so 0x squared, 0x cubed, then we get 1x to the 4th, and then 0x to the 5th. Okay, so that's our polynomial that represents the shape vector. Similarly, we have a leaf vector. This one's obvious. Okay, so now we've got a polynomial represented in a finite field. Okay, and these polynomials in this tuple at this point, we've got a kind of a 3 tuple, at this point represents our binary tree. Okay, let's keep going. So now we have some funny tricks that we can pull. We have some funny tricks that we can pull, which is that we can evaluate each of these polynomials. Note that length is kind of a trivial, it's a constant. But we can evaluate the other two using Horner's method, just a standard, let's just go evaluate our polynomial, like let's go plug in some a value into it and go evaluate it on a random value. Now, in an interactive oracle proof, that random value is actually generated by a hash function of all the data that you passed into it using what's called the Fiat-Shamir transform. But if you're kind of modeling it outside of the random oracle model, you could imagine you could actually pass in any random value and be able to get a fingerprint of these from these polynomials. Okay, so we're going to take these polynomials and we're actually going to evaluate them on random elements, which is going to be, in our case, alpha 1 and alpha 2. To break this equation down a little bit for you, we essentially have our lambda term here, which is just representing our length, which is on the left-hand side. Then we have our center term, which is our dequfelt or our dequard. So this w is the term, right? So we know that we have a function of the length in terms of the number of terms we have, and so we can sum up the individual terms evaluated on the randomness at the appropriate exponents. Similarly, we can do the exact same thing for the leaf vector. And so, in other words, this is just plugging in alpha 1 and alpha 2 into the first and second equations. Okay, super simple. This gives us fingerprints, but we still have a 3-tuple. Okay, so now we can actually take this 3-tuple, which we call our interactive oracle noun fingerprint, and we can then do tuple compression if we want to treat it as a single value. We don't always do tuple compression. I'm just showing you a technique that we use often if we want to have, say, a single value that's representative of a binary tree. So you can use this, and this is very simple. You have new randomness A, B, and C, and you have length times A plus shape times B plus leaf times C. Now the key here is that the randomness, in our case, is deterministically generated based on the data you've committed to. If that wasn't the case, in other words, if you had not committed to all of your data, you might have degrees of freedom to be able to pick randomness that might allow you to forge results. But because you've actually already committed to all of the binary trees that could possibly go into your computation and the order that they occurred, and you committed to a bunch of things, and I know I'm kind of bleeding in details of the actual invariance of Nock, so we can get to how we use some of these primitives around binary trees with Nock in a minute. But at a high level, if you commit to everything you need, then you can use these random values to get secure fingerprints and secure compression of these different components into a form that you can actually non-deterministically retrieve out the pieces. So this gets to something that's quite funky. We'll probably get to it later, and I'll just back up through the presentation. But at a high level, we can take the 3-tuple and we can compress it into one element, one finite field element, and pass it around instead of needing, say, a pointer to the data within our VM. Okay, so, and as we all know with Nock, cons rules everything around me. So many of you, and stop me if you don't, please somebody raise your hand if you're not familiar with this, are familiar with hash-conzing as an interpreter. Okay, not familiar with hash-conzing. Okay, great. So hash-conzing is a common technique used in Lisp interpreters to more or less be able to do very cheap deduplication across a memory arena, or often to be able to kind of compose operations lazily, as an example, that you might not necessarily want to do in place. So you can say, okay, we're going to do this operation, but we're not going to yet. Or you can say we're going to globally deduplicate items. We recognize this hash, so we don't need to store another copy of it. We're just going to store a pointer to this other one. Okay, so hash-conzing is a pretty common technique that's actually used in zkVMs regardless of whether they're binary tree based, because Myrtle trees are a very convenient and dumb and simple way to commit to structured data. And so often, even if they have kind of a regular old AST, they'll Myrtleize it and they'll turn it into a mast. However, every time they want to go decode an instruction, they need to go eat a ton of hash verifications inside their zkVM, which is extraordinarily inefficient. Now, hashing's not that inefficient in a normal context, but in a zkVM it's terrible, because the whole point of a hash function is that it's hard to calculate. And so, I mean, that's not the whole point. It's also collision resistant, blah, blah, blah. But often the way you receive collision resistance is by having complicated structures like S-boxes and other things that, at a high level, require you to have multiple rounds of arithmetic operations being performed on something. And, well, this is expensive. There are ways to speed it up, but you can't get around the fact that doing things that are more expensive in an arithmetic machine is going to be more expensive. And so everybody else destructures data using Myrtle trees, or even worse techniques, to be honest. Like just saying, well, do we really care about succinctness? We're just going to have all our memory be public. You can just see all the memory at every point. You can just go query it. Okay, so let's kind of go into things a little further. So because we have this beautiful relationship right here and here, where we're able to represent any individual tree as a sum that is based on its length as a polynomial. If I want to take another binary tree and slap it on, right, and cons this one to it, right, and form a new binary tree where, say, let's go back to the very beginning. If I want to take a new binary tree, let's say it's the same one. What if I want to slap another one of these trees on this one? So this one's the left-hand side now, and this one's also the right-hand side. If I want to do that, well, on the one hand, I've already talked to you guys about, well, what would it look like to do this? Well, we've got a valid deke word. We can put a 0 and a 1 on either side, and then just copy the inner body. Again, now we've got the shape, right? And then we can just copy 0, 6, 21 and 0, 6, 21, do it again. Okay, but how would we represent a verification of that? How would we verify that we had done that in a zkVM context? So at a high level, instead of needing to do something like hash-conzing, we are able to do cons via exponentiation. So you notice how alpha 1 and alpha 2 here are being exponentiated based on the sequence, based on the sequence number through the polynomial. What we can do is we can exponentiate the left-hand side, and forgive me if I'm off by 1 or something, more or less by the length of the right-hand side. And then just be able to add them up. There you go. We just did cons by exponentiation. All we did is exponentiate, multiply that whole polynomial by the exponent factor one time. Then we did it again for this one, and then we just added them. That's extraordinarily cheap in a zkVM. That's one multiplication, an exponentiation, which you can batch, and then an addition, which again is even cheaper. Okay, so this is, nobody else is doing this. This is nuts. So we're only able to do this because everything we interact with is a binary tree. We don't have anything that's not a binary tree. In fact, we hate things that aren't binary trees. Okay, so let's talk about just some cute examples. What are we able to do with this, right? What are we able to do with this? Well, we can't just prove little silly Nock programs. We can actually performantly prove real Hoon that you can go compile against our standard library. And starting on, I think the hackathon starts August 28th. Starting on August 28th, you're going to be able to start building programs that compile against our standard library. We'll be releasing our standard library with a variety of utilities that you can go play with. And you can send off proofs to our prover, which will be running on the network with our crazy custom interpreter, which will keep modding to be able to do the things it needs to be able to do for everyone. So this is an example of Fibonacci in Hoon. It's pretty simple. You've got your function. It takes in, how many times are we going to calculate Fibonacci? We start with x and y, which are 0 and 1, just because that's the base case of the Fibonacci sequence. Then we have a loop starting with the bar hep. Then we have a base case, which is of course the what call, which says, well, if n is 0, if we're done calculating, just return x. And then we just recurse through the loop, adding x and y, modding y to be x, and then we just say, well, let's decrement our counter until we hit 0. Okay, so I'm just going to show you guys a little proof of this, but a little bit silly. But you can see this is the same program, right? You see this fib file up here that's been scried that we've printed. Okay, so we're going to slap that against our flib, which is our finite field standard library, where we build up similar definitions that you'd be used to in Hoon.Hoon, not precisely the same because it's built around finite field arithmetic as the base of the increment case rather than unsigned big-int arithmetic as the base case. So not precisely the same. But then we essentially can say, let's go slap it against it, which lets us compile it and get a gate that we can run. And then we can actually run this against our FOC interpreter, which is our finite field Nock interpreter. This is just a funny name. We're going to change it. And so we can see, hey, we're going to go calculate Fibonacci for 3, just as a small, tiny little case. And you can see we get some printouts from our zkVM engine. It says, blah, blah, blah. We do all our tests. We compute various parts of this, and I can tell you about it if you want in the Q&A. Then we get a bunch of printouts. And then we say, wow, we got a proof out of the other end. And, well, the left-hand side of this proof is the actual result. And the right-hand side is, of course, the big old proof data structure, which you can go verify. And so at a high level, you can see we've got these tar and tar. We can see hep was 2, which is what we would expect from having done 0 plus 1, then 1 plus 1, et cetera. Or we did 0, we did 1, and then we did 1 plus 1. So that would be the third case. And then we can verify our proof. It says, yes, And that's all good. And many of you will be able to do this in just a few days. And hopefully you can do things that are even more fun too. All right, well, that is where we're at. Thanks, y'all. I'm happy to take questions.
Question?
So in the thing that you just made at the very end there that verifies that the third Fibonacci number is 2, to what extent does that original Fibonacci gate lie in that object?
Does it what?
Or to what extent is that Fibonacci gate represented in the verifier?
Oh yeah, so it's in the proof stream. So it's linked to in the proof stream. So you've committed to that program, and you can go say, oh well, is the program that I'm thinking that was run the correct one? Or you can like obfuscate the result and then reveal it later. Okay. Similarly, you can do the same thing with the output. So yeah, it's in the proof stream.
You talk about deterministic randomness, and that hurts my brain. Can you explain? Like those concepts to me don't.
Yeah. Okay, so what you can do is you can simulate randomness, and by randomness, I'm not saying that it's like literal entropy. What I'm saying is that it's not predictable. If you have a strong hash function and you've hashed all of the inputs and you've committed to everything that went into your program, then you're not going to be able to predict the numbers that come out of it. And that's called the random oracle model if you want to like go like bash your head against the wall with it. I can bash my head against the wall with you.
Any other questions? Oh.
So given that you're using finite fields, if I'm doing some kind of computation with large atoms, I would need to change that or rewrite that?
So what we have is we have support for unsigned 32-bit arithmetic. And what we can do is we are actually in process this week of writing a library around being able to do big int arithmetic in terms of lists of unsigned 32-bit integers. So you would probably need to like mess with it a little bit, but you wouldn't need to do anything crazy.
Does this mean you can just like parse all of the L2 logs and just resurrect all L2 planets with this?
Does this mean that I can parse the L2
Because then you
logs?
only have to do it once, and then you just have a verifier for everyone, and then you can just bring them all back into L1.
Okay, so you could do this. You would likely need to be very clever in the transpilation step in Tiny.
Right.
And if you weren't very clever, then it wouldn't really mean much.
Right.
Because the semantics of the, well, so I'll tell you something that is very speculative and likely won't amount to anything, just to see if you like it. But Edward has been talking to us this week about the possibility of actually simulating regular old Nock inside of our zkVM. You could imagine running a regular old Mink using our big int arithmetic library and actually having increment implemented in terms of our U32 big int chunk library. You could imagine this. Now, whether this would make any sense to do, I'm a little skeptical personally, but you could imagine it as a way to do this without needing to be really clever with the transpiler and just take something like that already exists and do it. Yeah.
Could you give an example of how you might pass around proofs, like sort of in a little bit more of a practical, like how would you consume this into maybe a really basic app? Who do I give the proof to? Yeah.
Sure. So let's say that you and I both lock up 1 Bitcoin. Or let's say we do it on ETH or something silly, like wrapped Bitcoin, right? And so let's say we both, let's say we just do an ETH. Lord help me. So yeah, let's say we lock up 1 ETH each on chain. Okay. You could imagine that we then have urbits, right? And you could imagine that we wanted to play a game of rock, paper, scissors with no trust. And then at the end, either one of us could submit the proof to the contract saying that the game really did happen the way that we said it was. Okay, so what we could do is you could pick a nonce. I could pick a nonce. You could commit to with a hash, a signed hash, in fact. your move and your nonce. I do the same with my signature and my hash, my move and my nonce, right? We go share that with each other. Now we have both of the ingredients. Now we both reveal our nonces. Okay, so until we've both revealed our nonces, neither of us know if we've won, right? So we're going to both reveal our nonces. And then whoever the winner is, they can go make a ZK proof that the game was conducted successfully based on our signatures and the hashes we committed to. And now look at that. You can go unlock the money and get the 2 ETH, and the other person loses all their money. So you can imagine building like cute little games out of this, just as examples that involve like basic cryptographic primitives, and then being able to have trustless, verifiable results thereof. Now similarly, now that's just a cute little toy example, but you can imagine composing more complex things, for instance, like one-of-n voting. You could imagine composing something like a ring signature using a mix of like committed public keys and ZK proofs. Similarly, well, you can imagine building like cute little games like Battleship or anything really that has information hiding. These are all interesting questions. Similarly, there's fun problems that you can solve that aren't just like scalable, trustless computation, but that are rather kind of more in the vein of things like dark pools, where you say want to conduct a bunch of financial transactions on behalf of a bunch of people, but prove that, hey, I actually did something proper at every time step, like I actually matched the orders properly at every timestamp. I mean, Tacen is very involved in this sort of thing. There's many use cases that look a lot like this, and there's a lot of others in games as well that are super obvious, but games are really interesting as an example because gaming is really just simulation. And so if you can get good enough at simulating reality, well, I mean, you can start doing things like ZK physics as well. And so that's where things kind of get silly. I believe I've posted this on Twitter, but we have a grantee that's been working on well, machine learning in Hoon, I believe, with our man Neil Davis over here, and one of the guys at Native Planet, Mopfel. And so it's really, really wonderful because the result she's gotten just recently is she's been able to prove MNIST with a, or not prove, I should say. We don't have it running in the zkVM yet. But she's been able to run MNIST inference properly. So detecting handwriting samples using a machine learning model that she read in just from Clay. So these are the type of use cases where you can take something that you want to do, some task that you want to do that you might want to just prove to someone else, either trustlessly or with information hiding, and then be able to commit to data, et cetera, and then have a trustless proof at the end of the day. Yeah.
Cool. Thank you.
Thanks, Logan. Two-part question. So one is, what kind of performance gains do you get if you were to implement Fibonacci and EVM stuff or whatever?
Yeah, so okay, keep going.
No, go.
Okay.
I'll ask my second question.
Yeah. So with our model, you may be familiar with something like MyDinVM. Mm-hmm. It's a well-known Stark example. So we've been building and prototyping just with basic Stark primitives because we think it's a fun way to kind of keep ourselves honest mm-hmm. and not get too fancy with the cryptography too fast. Because frankly, like AIR is so restrictive that if you can build something really, really competitive in an AIR context with so many other people building an AIR, it's really, really obvious that you're actually onto something in terms of the model, not just your implementation. And so we're pleased to say that in terms of base columns in our zkVM, so Miden has a notion of the base columns that they use to keep track of their stack operations and many of their other operations, and then they kind of have their built-ins columns, which built-ins would correspond pretty directly to jets for us. Mm-hmm. So for our base columns, at this point, I hesitate to give you the number because it's changed this week, but we're well below where Miden's at, and we're really, really pleased to say that. And I can tell you concretely, Miden's far more efficient than any of the ZK EVM solutions.
Well, like longer term, do you expect like an order of magnitude kind of improvement, or?
With the lasso work, maybe.
Okay.
Because as we were discussing, it's not just about instruction set size; it's about decomposability. Right. And it's hard to beat binary trees for decomposability.
Okay, and then second part are like, what are the obvious immediate like applications, and in particular, seems like you could build kind of like an Ethereum-based layer 2 with Hoon smart contracting pretty quick on this, like a ZK L2?
Someone could if they wanted to, yes. Yes, that would be a thing that someone could do. Similarly, they could build other application-specific use cases that they wanted to have, say, checked in and validated on a chain of their preference.
Okay, thank you.
Hey, so you mentioned Zorp is going to be running a prover. Say I have free computing power to just burn, right? Is it going to be possible for us to run our own provers? And if so, what amount of computing power are you looking at to run a prover?
Yeah. So right now we're just using Mac Studios, and they're great for the test. Now that being said, we're not open sourcing our prover yet. We are going to, and you'll have plenty of use for your computing power, and it'll be obvious. So yeah, you'll see it. Would love for you to use your computing power, build a bunch of proofs. It'll be wonderful.
Good stuff.
Any other questions?
Can you talk about how there's this interesting case where scries and the balanced scry namespace makes some guarantees about referential transparency, but it also seems like you can't really feed a fake 12 into this scheme that you're talking about. Can you just address like what happens with that sort of model with
Yeah. So this is a question for us. So with Nock 12, you run up against a question in the start model. Now, in a lookup table-based system like, say, Lasso, or even more conventional lookup table-based systems, this question is not always as important. But in a system built around like a referentially transparent namespace, if you can commit to the namespace out of band in the proof, then you can basically treat queries into the namespace as either something like a Merkle path authentication. Basically, you fall back to that like slow hash verification, or you can treat it like an oracle. And you're really at your leisure to do either one. And frankly, stateless reads into arbitrarily large data are a much better fit for lookups than they are for any easily accessible primitive that you would get in a start. But we're in process of more or less evaluating next steps for our prover engine and moving beyond just the naive like start approach. So in that regard, while I don't think you're going to get a free lunch with scries because they're not real, I mean, it's not a real instruction. It's a fake instruction that's used for convenience. And as such, it breaks the computing model. So you're not going to get a free lunch with it, but I mean, we have an approach that we could do if we wanted to. Right now with 12, we're just prioritizing other things. And as the prover engine that we have gets more sophisticated, I expect that it'll get a little better. Sure.
Hey, yeah. So given the Nock maximalism, right? What's next in terms of like writing programs that compile to Nock, potentially outside of Hoon?
Yes. That's a great question. So we're building a language, and we're codenaming it Acacia. That is directly inspired by Swift, but won't seek to religiously uphold Swift's entire paradigm and standard library. But yeah, we're building a language that's inspired by Swift that will be, I think, a much more accessible to get started with language that will compile down to Nock than Hoon is. But I do expect it won't be as productive or expressive.
And then a follow-up question: how are you guys planning on distributing this library for testing out your suite?
Yeah. So we'll basically have a testing desk, and we'll distribute that over the LiveNet. We expect that you should probably put it on a moon or something that you are happy to throw away, because we're going to ask that you use a custom binary for it.
Gotcha. Thanks.
Any other questions? No? Let's give it up for Logan, everybody.